Hi class, we are on 20.3 now. This is we're going to be discussing voltaic, also known as galvanic cells. These are generating electricity from spontaneous chemical reactions. So in electrochemical cells, electric current is a flow of electric charge. It's really electrons flowing. And there's two types of electrochemical cells. We're going to look at voltaic in this section. This has to do with spontaneous chemical reactions, and we use these electrons, we use these reactions to have electrons flowing through a circuit. In this case, if you remember in previous chemistry, when you first learned about electrolytes and so forth, you could, in a sense, think about specific chemical reactions, but a light bulb hooked up to an electric circuit, and the light bulb would light up based on the chemical reaction that's spontaneously done. This is dealing with oxidation reduction half reactions. They are kept in half cells, so they are separated from each other, but there is things connecting them. Electrons flow through a wire along with ion flow through a solution that constitutes an electric circuit. And of course, there'll be pictures to show this. It requires a conductive solid electrode to allow the transfer of electrons, and that's through an external circuit. That's where the light bulb would be, so you could see the flow of electrons. You wouldn't see the flow of electrons, but you would see the light bulb lighting up. And the electrode is made of metal or graphite. Again, we're going to cover that. And it requires an ion exchange between the half cells of the system, and that is going to be an electrolyte that's going to allow this ion exchange to allow this to keep flowing. Okay, so I said there's two types of electrochemical cells. The voltaic is a spontaneous chemical reactions, and this creates a flow of electrons, also known as electricity. It is two half cells connected in a way that the electrons flow from one electrode to through an external circuit that's above the half cells, and then to another electrode. The ions flow through an internal cell connection. So that's what the salt bridge is, and that's connecting through the solutions. There are also electrolytic cells. This is for non-spontaneous chemical reactions, and it needs an external source in order to force these non-spontaneous reactions to occur. We're not going to cover that in this section, but both involve redox reactions, and they are in half reactions that are separated out of each other. So with the voltaic, we have, for instance, if you look at, so voltaic is an electrochemical cell which is spontaneous reaction generates an electric current. So we're putting together things that we know will react spontaneously. Some have, I'm not even going to go there yet, but a spontaneous. Key thing, spontaneous. We will get electricity from this because of the electrons that will flow. In this case, we're going to look at zinc and copper. And so we're going to have a zinc bar and a copper solution in separate containers, and they're going to provide the connections for a flow of electrons. It's easier if I just show you. So let me go through the reaction first. So the reduction, what is the reduction? The reduction is being reduced. I should have put this one on top. I like the oxidation first because I like to show that the electrons, where the electrons are coming from. And the electrons are coming from the zinc because the zinc is in a solid state and it is going to become in an ionic state. And when it becomes an ionic state, it loses 2 electrons in that time. And then what happens, those electrons flow through the above the half reactions, and they go into copper. Copper is an ionic state, which will then join together and it will become a solid state. So I like to show where the electron's going. So this is kind of backwards, in my opinion. But that's what you're seeing. The 2 electrons flow from one to the other. So zinc starts out as solid, ends up ionic. Copper starts as ionic and ends up as a solid. So let me show you. You can kind of see here. If we were in person, no, I don't even go there either. Okay, so we have a zinc strip here. This is a zinc. This is what I'm actually discussing, but they have it separate. So this is 2 half reactions that are separate from each other, but this is not exactly this. This is not showing the full thing here. But what this is that this is a zinc. This metal strip is made out of zinc, and it's in copper sulfate solution. Again, this is not the same as what we're showing here, but you can see that it's going to react. That's what they're trying to show. So the zinc is going to come out of solid into solution, and the copper, which is blue, will lose the blue because the copper is now going into a solid and out of solution. So if you let this go long enough, the blue will go away because the copper is going away and it's going back into a solid. It's not staying in ionic form. That's why you see at this next picture, you see this black kind of forming. That's because it's going into a solid form here, where here it was an ionic form. So this is showing here the solid atoms, the zinc atoms, and what it's doing is they're coming out of the solid. So this solid is actually, in a sense, degrading, or what's another way to, you know what, I can't think of the word right now, but it is slowly going away because it is leaving the solid. So maybe like in a sense of rusting, and the ions are then, the copper is going to take the electrons, and what you see, it's going to attract itself to the surface of the metal strip. So that's what you see, the blue. You see how blue this was? So you see how blue it is, and it's not as blue. If it goes long enough, it'll keep, the blue will eventually go away completely. So what it is it's exchanging places. In this case, this is a salt bridge, and the salt bridge is in contact with both solutions. This prevents the reactions coming together, because then the reactions would occur on its own. But they want the flow of electrons. So this is in a zinc solution in a zinc electrode, which is a metal solid. And it's going to, the electrons always flow from negative to positive. And that makes sense because the negative has the electrons. The positive is deficient of them. So it's going to flow from, well, in this case, there's different kind of electrochemical cells. In the galvanic, this is how this flows. So I shouldn't say always, because that's not true. The electrons flow. You see the light bulb? That's telling you the electrons are flowing, and then it goes into here. And the solution will then come together, the electrons will come together with the copper and make a solid. So, excuse me, I went too far. So when we look back here, let me show you. These are called electrodes. So this is because this is the zinc, this is the one that's oxidized. This is called an anode, and this is called a cathode. And that's because this is where the positive side is. And this is what a half cell. So they're not together, or in some cases you can, but there's something preventing them from interacting, the solutions. And so this is basically a copper metal strip, but we call it the copper electrode. And this would be a zinc metal strip, and this is the zinc electrode. And the electrons always flow from the anode to the cathode. So the anode is made of the metal that is oxidized. The cathode is made of the same metal as is produced by the reduction. If the redox reaction involves oxidation or reduction of an ion to a different oxidation state, or the oxidation or reduction of a gas, we may use an inert electrode. An inert electrode just means it doesn't react. We're not using something that's going to participate in the actual reaction. So remember, in terms, it's not really, but you think of like a catalyst, where catalysts help speed up a reaction, but it didn't didn't participate in the reaction. The inert electrode is not helping speed up a reaction, but it is there, but it's not participating in the actual reaction. But it provides a surface on which the transfer of electrons can take place. So it is instrumental with helping, but it does not take place in the reaction itself. So that's what inert means. So an anode electrode, where oxidation occurs, more negatively charged electrode, in a voltaic cell. So this is a big thing, voltaic. And in this case, for the example, it's zinc. Cathode is electrode where reduction always occurs. That means it gains electrons. More positively charged electrode, and that's where the copper was, and it will form as a solid, a salt bridge. And that's what this upside down kind of U looks like. Oh, you can see a better one here, that you can see it. And a salt bridge connects the two half cells, and it's a strong electrolyte. So the salt bridge is a tube of an electrolyte gel, and it connects the two. Let me show you a picture. It might be easier to show. It connects the two half cells and allows the flow of ions, but prevents the mixing of different solutions. Because what happens is that there's a buildup of the other ion that is connected to either the copper or the zinc, and there's a buildup. And what it does is it allows them to flow in order to prevent this buildup from having too much of a buildup, is what I should say. Okay, so if we look here, what this is that we have two half cells. I know I've already said this, but I'm going to repeat myself, that are connected internally by the salt bridge. And here is the anode, here is the cathode, and you can see the electrons go this way into the cathode, and that's where you see the light flowing. But what is the salt bridge for? Well, what happens is that as zinc ions continue, because now we have zinc ions here, right? So if we have enough of them, the zinc ions produce, the zinc ions build up a positive charge here. And similar on this side, the copper ion plate, as the copper ions plate out of copper metal, the solution builds up a negative charge. And that we don't want that to happen, because it'll eventually stop the ions. So eventually what will happen is this will just stop. It'll stop unless we have, it will stop unless the positive ions can move from the zinc half cell to the copper half cell, and the negative ions from the copper half cell can move to the zinc half cell. So we need the ions to keep flowing. So even though we have electrons up here, we also need the ions to keep flowing to prevent the buildup that is here from what's actually happening in order to get this going. So, excuse me, it's necessary that the ions flows occurs without mixing of the zinc ion and the copper ion solutions. If they were to come in contact, then we would have this react together, as I showed you in this picture. Once we put the copper solution with the zinc, there's just going to be reaction, but we're not using the electrons the way we want to. So this allows the flow of ions in order to prevent the buildup of the charges here, so that this can keep going. So the definition of a salt bridge is a tube of an electrolyte in a gel that is connected to two half cells of a voltaic cell. The salt bridge allows the flow of ions, but prevents the mixing of different solutions that would allow direct reaction to the cell reactants. So we're allowing this reaction, but actually doing work. We're getting work out of this instead of just a plain reaction occurring without being able to efficiently use it. Okay, so characteristics of a voltaic cell. The metal bars where the redox reaction takes place are called electrodes. That means reduction and oxidation. The source of electrons is the negative electrode. So the electrons flow from negative electrode to the, which is the anode in a voltaic cell, to the cathode, which is the reduction, which is positive. The electrons move through the wire towards the positive electrode, cathode. Reduction occurs at the cathode. To prevent the buildup of negative charge in the cathode compartment, ions from the anode and cathode solutions flow from the salt bridge. Okay, the wire and the salt bridge connect the anode and cathode. That is to form a complete electric circuit. That's where we see the light bulb. Electricity is produced by the movement of electrons that go through the wire from the anode to the cathode to transfer, and that's where the reduction takes place. The driving force of the flow of electrons is the electric potential, or electromotive force, and the electric potential is measured in volts. Now I'm going to go over these last two in a couple slides ahead, so I'm just going to go over the review of these. Both oxidation and reduction are taking place at the same time, though not at the same place, and they have to take place at the same time because the electrons have to go somewhere. So if they get pulled out of one substance, they have to go into somewhere. They have to go somewhere. The reaction is spontaneous, so electrons move from the anode to the cathode spontaneously, meaning we don't need any help with this. The chemical energy of the reaction is transferred into electrical energy. So we're using chemical energy and transferring it into electrical energy, which can then be transformed into light or mechanical energy. That's what the light bulb that you see. So electric current. Electrons flow through a conductor in response to electrical potential difference. This is the difference of water flowing down a hill, because it's using the gravitational potential energy, because the water uphill wants to go down to a lower point. So it's going to just flow on its own. It's always just going to flow on its own. It's never going to flow upwards. It's got a lower potential energy at the bottom than it does at the top. So we can think of this as the same way. Really, work is needed to move electrons in a wire or move ions through a solution electrode. So it's not just, even though the reaction is spontaneous, there is still work that we need to have done. So think of this, and I know it's not on the slide, but water moves from a point of high pressure to a point of low pressure. A pressure difference is required. And it's the same for electricity. But the way we look at it is an electric charge moves from a point of high electric potential to, so think of that as high electric pressure if you have to a point of low electronic potential or low electronic pressure. So where it's lower pressure. It's going to travel to high pressure from low pressure. If you remember anything about gases too, it's going to, high pressure, it's always going to try to go to a lower pressure if it's given the volume to do it. The work needed to move an electric charge through a conductor depends on the total charge moved and the potential difference, which is on the next slide, is the potential difference. So there's got to be a charge and there's got to be a difference. So what we're looking at here is there are a current. So a current is the number of electrons that flow through a system per second. And the units that we use for the current is ampere or amps. I'm sure everybody's heard the word amps. That's the current. That's the number of electrons that flow through a system per second. So how many amps? The higher the amps, the higher number of electrons that are going to flow per second. The lower the amps, the lower number of electrons that are going to flow per second. And 1 amp of a current is equal to 1 coulomb of charge flowing each second. 1 amp is equal to 6.242 times 10 to the 18 electrons per second. Okay, so potential difference, sorry. Potential difference is the difference in electric potential. So think of electrical pressure between 2 points. We measure this in volts, so that's the unit of potential difference. The greater the current, so this current and voltage go together. So we looked at current here. The greater the current, the lower the voltage. Cell voltage has a max value when no current flows. So when the current's not on, you'll get the max voltage possible. However, the stronger the current, the voltage is going to keep going down. You're going to get a lower voltage on it. And what does voltage have to do? Voltage is the units for potential difference. So the difference in potential energy between the reactants and the products. Remember, we're dealing with electrical energy here. So we have a difference in reactants and products, and that difference is what we measure in volts. So the amount of force pushing the electrons through a wire is called the electromotive force, or EMF. The max potential difference between the electrodes of Voltaic cell. We can measure this by using an electronic digital voltmeter. It's not listed in your book, but I'm just telling you this. We can use this measurement to also determine the anode and the cathode, because the volt gives a sign, it gives other information. Through that we can actually determine which is the anode and the cathode on this. Okay, so the difference in potential energy, more of a review, is the difference in potential energy between the anode and the cathode in Voltaic cell is called the cell potential. We're going to actually start doing some numbers with this next section. So if none of this is making sense, hopefully it will be when we actually do some problems. The cell potential depends on the relative ease with which the oxidizing agent is reduced at the cathode and the reducing agent is oxidized at the anode. So here's the thing. When we use zinc and copper, this happens spontaneously, but each of these have values to them on how easy they are oxidized and how easy they are reduced. So if we change out zinc for something else that is not as easily oxidized, then the value is also going to change. The potential will not be as much. Let me just say the potential will be different compared to what was zinc, because zinc is so easily oxidized. And the cell potential under standard conditions is same with standard. Remember, standard means, think of like standard temperature and pressure. We have certain conditions, and that's how when we investigate certain things, we look at it under certain conditions. Well, EMF is no different. We have a standard for it, and it's at 25 degrees Celsius, 1 atm for gases, 1 molar for concentration of solutions, and we sum of the cell potentials for the half reactions. Again, we're going to cover more of this. This is just the beginning. Okay, so let's do a problem. Which statement best captures the difference between volts and amps? And I like this one because maybe it gives a better idea of what you're actually dealing with. I'm just going to jump to the answer. The volt is a unit that quantifies the difference in electrical potential. So let's think of it this way: the difference between the reactants and the products. And the amp is a unit that quantifies the flow of electrical current. In a voltaic cell, which directions do electrons flow? I'm going to cheat again and just go this way. From higher potential energy to lower potential energy. Remember, in chemistry, everything is about stability and the lowest stable level it can get to. So it's always going to travel to that. And in this, unless forced not to, which will happen in another electrochemical cell we'll look at. But in this case, if you left to spontaneously happen, it's going to go to a lower stable level if it can. The lowest energy that still makes it stable. All right. So convenient way to show what is happening in a voltaic cell is to use standard cell notation. So I'm going to do a review of this on the next page. In a standard cell notation, the flow of electrons is shown from left to right. So left to right, starting with the composition of the anode. So when you see this, the anode is always going to be written on this side. The cathode is going to be written on the other side. So that's something you should definitely know. Now, what do these little lines mean? So single lines indicate a phase separation. And when you can see this here visually, it goes from solid to ionic. Here we go from ionic to solid. And the double lines indicate a salt bridge. Doesn't tell you what the salt bridge is, but that there's a salt bridge there. So let's go a review of it. Shorthand representation of electrochemical cell. Oxidation half cell on the left, reduction half cell on the right, separated by two vertical lines, indicates a salt bridge. Substances in different phases are separated by a single vertical line, and which represents a boundary between those phases, and you can see it right there. If a multiple species are in the same phase, a comma is used rather than a line. And I gave an example here where you can see there's comma right here and right here. So you can see that. And often use an inert electrode, and I'll show you on the next page more about that. And double line means a salt bridge. Electrode, electrolyte, electrolyte, electrode. So you can see where this would be the salt bridge, where you would have the anode, salt bridge, what it's made out of, and then the cathode, if you had to give all that information. So we use an inert electrode in some cases. Why? Because they don't react. They help participate in the reaction by helping it, but they don't actively participate in the reaction themselves. So again, like similar to a catalyst, a catalyst helps speed up a reaction, but it doesn't participate in the actual chemical reaction. You don't write it out in here, the chemical formula. So in this one, we see that the half reaction involves manganese that goes from an oxidation state of +7 to 2. So it has gone from, it is being reduced down. It's gained 5 electrons in order to be reduced down. We use an electrode that will provide a surface for the electron transfer without reacting with MnO4 minus. Platinum works well because it is extremely non-reactive and conducts electricity. So that's where we can use something that's inert but will still help the reaction to go. And as you can see down here, here is the cell notation, and you can see here's the electrode right here. The inert electrode, yes. Can't get this right. So you see the cathode is platinum, but it's actually just having the electrons form on it, or it's helping participate with the flow, but it's not really actively in the reaction itself. Okay, so write cell notation based on the description of the following voltaic cells. So here is given enough information that you should be able to try to write these out if you're given this information. So I'm just going to jump to the next page. A couple things to remember. Anode is written first, with the oxidation takes place as first. The cathode is written next. If there's a salt bridge, there should be 2 lines, and if there's a phase change, there's 1 line. So in this case, silver ions are reduced, so this is telling you this is a cathode. Copper metal is oxidized, that's the oxidation. So the copper needs to be written first. So if it's going from, if this is the end result, then it had to be in a solid state. So here's a solid, here's a phase change, here's the ionic form of it, and it's in 1 molar. And then we have silver that is being reduced down, 1 molar, and it goes to a phase change with a salt bridge in the middle. Here we have iron 3 ions are reduced to iron 2 ions in the presence of a platinum electrode. So here it's going to, the platinum electrode is going to help this happen, but it's not going to take really actively take place in it. And tin is oxidized to tin 2 under standard conditions. So this is standard, which means that it should be 1 molar. So we have tin that is oxidized to tin 2. So we have as a solid, goes to tin 2 and 1 molar. Here's a salt bridge. And then we have the cathode. So the cathode is platinum. It's inert. So it's helping this, but it's not actively taking place. It's not helping the reaction itself. Then we have iron 3 to iron 2 being reduced, 1 molar and 1 molar. So this is examples of how to write cell notation. Okay, so here's a review. Reactants that undergo spontaneous redox reactions when in direct contact with each other will also react spontaneously when suitably connected. So they will still react, but we're trying to get work out of this so we can separate them out into the half cells so we can make the electrons flow into something that we can use. A complete circuit is necessary for a voltaic cell to operate. That means that we need a metal wire for the flow of electrons, and we also need a salt bridge for the flow of ions to be able to stop the charge buildup in the solutions. A voltaic cell produces electricity from a spontaneous redox reaction. The oxidation half reactions occur in the anode. The reduction half reactions occur in the cathode. And electrons flow for voltaic cells from the anode to the cathode. Standard cell notation summarizes the flow of electrons in a complete electrochemical circuit.